consider the function f of x is e to the power cosine of 2x. X is greater or equal than negative pi over 4 and less or equal than 5 pi over 4. A. Find the coordinates of the points on the curve y is f of x where the gradient is 0. So gradient of the curve is the gradient of a tangent, and we know that the gradient of a tangent is equal to the derivative at the point where it is drawn. So we should find what? Derivative and just equate it to 0, and hence find points where derivative is equal to 0. Or it's actually the same as stationary points, and stationary points are candidates to be maximum or minimum, or to be turning points, the turning points. So let's find derivative. df over dx becomes, you can say, e to the power, and you remember that e to some power we consider as a function of a more complicated argument, and we use what? Chain rule for more complicated argument. And how to apply it? To apply this rule, we use a formula which is given in the booklet for e to the power over x, and it says that it's the same. But since it's a more complicated argument, there must be this argument, it must be multiplied by this argument derivative. And cosine of 2x, it's actually also cosine of more complicated argument without no power. So it's sine of negative sine of 2x multiplied by 2x derivative. Or you remember that if it's a function of ax plus b, just a arises in front, and you keep the same argument. So it becomes negative 2 sine of 2x and multiplied by e to the power cosine of 2x. And it should be equal to 0. E to some power never equals 0. Its graph looks like this. E is greater than 1, so it looks like this. It's in general exponential function a to the power x. If a is greater than 1, it looks like this. When a is greater than 0 but less than 1, it looks like this, but it always greater than 0. It asymptotically falls on x-axis. It means it tends to y is 0, or horizontal asymptote is y is 0, but it never equals to negative value. So it to be equal to 0, it's possible when sine is equal to 0. And how to solve sine is 0? Solution is sine is 0, it's what? 0 or pi, and we can combine these two solutions as pi k, where k is integer, and you can see when k is 0, it's 0, when k is 1, it's pi, when k is 2, it's 2 pi, and hence you move between two consecutive roots by adding pi as required, and hence x is pi over 2 k. And hence solutions are, since we need from negative pi over 4 to 5 pi over 4, when k is negative 1, it's too much. When k is negative 1, it's negative pi over 2, which is less than negative pi over 4, so it's not a root. So when k is 0, x is 0, it's a root, and when k is 1, it's pi over 2, and when k is 2, it's pi, and when k is 3, it's greater than 5 pi over 4, so it's not a root. So there are 3 roots, but it is required coordinates of the point, so we need y coordinates for each point. So when x is 0, or we can write just y of 0, becomes what? E to the power cosine of 0, it becomes just e. So the first point is 0, e. The second point, it's when x is pi over 2, y becomes what? E to the power of cosine of pi, which is -1, so it becomes e to -1, or 1 over e. So the second point, pi over 2, 1 over e. And the third point, y of pi, it's what? It's cosine of 2 pi, it's 1, so it's also e. So pi e. And these are required stationary points, or points with zero gradient. The next. Using the second derivative at each point found in part A, shows that the curve y is f of x has 2 local maximum points and 1 local minimum points. So we need the second derivative, and second derivative, just derivative of the first derivative, and it's the first derivative, and let's find the second derivative. So the second derivative becomes, we can see a product, so we apply a product rule, so it becomes -2 sine of 2x derivative times e to the power of cosine of 2x plus or minus 2 sine of 2x and e to the power of cosine of 2x derivative, which becomes sine of 2x derivative, it's what? Cosine of 2x, and 2x derivative 2 arises, so it's -4 and times e, and -2 sine of 2x, and e to the power of cosine derivative, it's actually this again, so it's -2 sine, so it's plus 4 sine squared and e to the power of cosine of 2x. Well, let me check. Plus sine squared, correct. And the second derivative at point 0 here, so there is only x here, so we just write the second derivative at 0 becomes what? Sine of 0, it's 0, so it disappears because it's 0, and we get what? -4 cosine of 0 e to the power of 1, so it's -4 e, which is what? Which is negative, hence what? 0 e, is a what? Local maximum point. Why? Because the second derivative to be negative implies what? A shape or concave down, shape to be concave down, and if it's a concave down, it's maximum. Or you remember, if the second derivative is less than 0, it's a maximum, local maximum point. And the second derivative at pi over 2 becomes what? -4, and cosine at pi, it's -1, and e to the power of what? Also -1, and it becomes 4 over e, and it's what? It's positive, hence our point pi over 2, 1 over e is a local minimum. And the second derivative at pi becomes -4 cosine of 2 pi, it's 1, and e to the power of 1, so it's and again it's 0, and for the previous also 2 times pi over 2, it's sine of pi, which is also 0. And here it's just negative for e, which is less than 0, hence pi e is a local maximum point. The next, sketch the curve y is f of x for x is greater or equal than 0 and less equal than pi, taking into consideration the relative values of the second derivative found in part B. So what is the second derivative? And we need with respect to values of the second derivative. And what is the second derivative? It's the derivative of the first derivative, and the first derivative shows what the rate of change, and we know that rate of change is gradient over tangent, and hence second derivative shows how quickly or how rapidly gradient over tangent changes. And also second derivative says us about its concave up or concave down. So we need from 0 to pi. And actually we can calculate values of a function at end points, and function at 0 becomes what, and function f of x is e to the power of cosine of 2x, and function at 0 it becomes what, just e. Function at pi over 2 can be easily calculated, so we can calculate this midpoint. So it becomes what, e to negative 1 or 1 over e, and function at pi is what, cosine of 2 pi, it's also e. And with respect to the values of second derivatives, you can see that at the midpoint, second derivative is 4 over e, and at end points it's 4 times e, and 4 multiplied by e will be much greater than 4 over e. It means that at the midpoint gradient changes not such rapidly or more slowly, or at end or closer to endpoints, a gradient will change more rapidly, and hence and also second derivative at 0 is negative, so it means what, it's concave down, and at the midpoint it's concave up. And also we can consider this function, and we know that for cosine of 2x period is pi, because of 2 in front of x. And if we consider from 0 to pi, cosine looks like this. It will be one complete revolution for cosine. It changes from maximum to minimum at pi, and again to to its maximum value, and hence e to the power of cosine, you may suggest that it will do the same, so it will be maximum, minimum, and maximum. And since cosine is symmetrical for one complete revolution, so our curve also will be symmetrical. And again, taking into account the relative values of second derivative, since gradients will change more slowly at the midpoint, and hence a curve will change also not such rapidly here, but more rapidly it must be a bit wider here and symmetrical. It must be symmetrical and more rapidly closer to the endpoints. Something like that, and it's E, and it's 1 over E. Something like this. Definitely it must be a smooth curve. Okay. Sketch, so done. The next. Find the Maclaurin series for cosine of 2x up to and including the term in x to the power of 4. A formula is given in a data booklet, and it says that cosine of x is equal to 1 minus x squared over 2 factorial, which is 2, plus x to the power of 4 over 4 factorial, which is 24, and plus so on. Hence, cosine of 2x, and we just would substitute this argument for x into the formula of cosine. It may be absolutely any argument in general, so it becomes 1 minus 2x squared over 2 plus 2x to the power of 4 over 24 plus so on, and it is equal to, or we can write approximately equal what, 1 minus 2x squared plus 2 thirds x to the power of 4. And if you write approximately equal, you don't need these dots at the end. Done. The next. Hence, find the Maclaurin series for e to the power cosine of x minus 1 up to and including the term in x to the power of 4. So first of all, cosine of 2x minus 1 becomes what? It just 1 minus 2x squared plus 2 thirds x to the power 4 minus 1. It's clear that it's just negative 2x to the power 4 plus 2 thirds x to the power 4. And using or actually we can rewrite e to the power cosine of 2x minus 1 becomes e to the power of negative 2x squared plus 2 thirds x to the power 4. And using a series for e to the power of x, it is given in data booklet, e to the power of x is 1 plus x squared over 2 and plus so on. Hence, e to the power of cos of 2x minus 1 becomes what? You can see that e to some power, and you should consider this expression for x, and you should substitute this for x into this expansion, so it becomes 1 plus x, so it's negative or minus 2x squared plus 2 thirds x to the power 4 and plus 1 over 2 x squared, so it's negative 2x squared plus 2 thirds x to the power 4. In general, it's plus dots, or you can write approximately equal squared and since we need up to and including x to the power of 4, if we consider this, we can consider it in general it's plus higher powers, and you may consider actually you may consider here as a plus b squared, or in general you may consider as this expression is multiplied by itself, but you can see that we can get x to the power of 4 only when this is multiplied by itself in the second expression, or if you consider as a plus b squared, you can see that you can get power of 4 or less only when this squared. For other products you will get finally power of x which will be greater than 4, and we don't need powers of x which are greater than 4. So it becomes 1 minus 2x squared plus 2 thirds x to the power of 4 plus 1 over 2, 2x negative 2x squared, and it becomes 1 minus 2x squared plus 2 thirds x to the power of 4. It's what? Plus 4 over 2, so plus 2x to the power of 4. Yes, and it becomes what? 2 it's 6 over 3, so finally it's 1 minus 2x squared plus 8 over 3x to the power of 4. Yes, it's correct. Yes, hence write down the Maclaurin series for f of x. What is f of x? F of x is just e to the power of cosine of 2x. It's f of x is, and how it is related to this. You can see that this it's what? It's e to cosine of 2x divided by e. And hence e to the power of cosine becomes e multiplied by this expansion, this series. So we can write that it becomes, it is approximately equal to e 1 minus 2x squared plus 8 over 3x to the power of 4. Okay, next. Use the first two non-zero terms in the Maclaurin series for f of x to show that integral is equal to, and the first two non-zero are these terms. So this integral becomes integral from 0 to 1 over 10 e to the power of cosine, so it becomes e 1 minus 2x squared dx, and it's a constant, so it becomes e, and you can see that we can easily integrate it, and it becomes what? X minus 2 thirds x cubed, and since it's with limits, so it becomes from 0 to 1 over 10, and just substituting the upper limit we get what? E to the power of, multiplied by what? 1 over 10 minus 2 thirds, and 1 over 10 cubed, it's what? 1 over 1000, so it becomes 2 divided by 3000, and just minus 0. And let's just do a common denominator. Common denominator becomes 3000, and additional factor here, it's what? It's 300 minus 2 and e, and it becomes what? 298e over 3000, which is, we can divide by 2, numerator and the denominator, to get 149e over 1500 over 1500 as required. And that's all for this question.